Have you ever wondered how scientists measure everything so perfectly? From the size of atoms to the temperature of stars, in chemistry, measurement is everything. And today, we're going to make it super easy. In chemistry, scientists use a standard system called the SI system, the International System of Units. It helps scientists all around the world use the same measurements, so everyone understands each other clearly. Think of SI units as the universal language of science. First, we have length, measured in meters. Then there's mass in grams and volume, which we measure in liters. We also use Kelvin for temperature and seconds for time. Each one is essential. By using these same units, a measurement taken in Tokyo means the exact same thing in New York. We even have specific units for things like pressure and electric current. It's all covered. Sometimes measurements are very big, and sometimes they are very tiny. That's why we use prefixes. Prefixes are like shortcuts. They tell us how many times to multiply or divide the base unit. Kilo means 1,000 times bigger. On the other end, milli means 1,000 times smaller. Micro is even smaller, and nano is incredibly tiny, down to the level of atoms and molecules. Think of it like this: a mountain versus a human versus a tiny bacterium versus a single molecule. Struggling to remember the order? I have a fun mnemonic for you. Great mighty King Henry died by drinking chunky milk Monday night. Giga, mega, kilo, hecto, deca, base, desh, centi, milli, micro, and nano. See? Easy. Now, let's learn a powerful trick called dimensional analysis. It's the secret to easy conversions. It helps us convert units safely. Let's convert 15 centimeters into inches. Step 1, find the factor. We set it up so the unit we want to get rid of is on the bottom, like this. Centimeters cancel out, and we are left with only inches. It's like magic, but better. It's math. 15 divided by 254 equals about 5.9 inches. Perfect conversion every single time. Pro tip, always arrange your fractions so the unwanted units cancel out. That's the key. In chemistry, we measure many different things. Let's look at the big four. First is length. It tells us the distance between 2 points, like the length of this pencil. Next is volume. This tells us exactly how much space a substance takes up. Then we have mass. It's the measurement of how much actual stuff or matter is inside an object. And finally, weight. Weight is the force of gravity acting on that mass. Don't confuse the two. Mass and weight are not the same thing. This is a very common mistake in chemistry. Mass stays the same everywhere in the universe, but your weight depends on gravity. On the moon, you weigh much less because gravity is weaker, but your mass stays exactly the same. So if you travel to space, you'll still be the same you, just a lot lighter on your feet. Moving on, time is measured in seconds. It's the period between events. Density tells us how packed matter is. Think of a sponge versus a solid metal cube. The cube is more dense because its particles are packed tightly together. Temperature is actually a measure of how fast particles are moving. Fast means hot. Heat is different. It's the total energy of all particles in a substance. Remember, temperature is about how fast they move. Heat is about the total energy they have. Now let's convert some temperatures. Chemistry loves the Kelvin scale. Convert 25 degrees Celsius to Kelvin by simply adding 273. That's 298 Kelvin. For Fahrenheit, multiply Celsius by 9/5 and add 32. 65 degrees becomes 149. Scientists use these different scales depending on where they are and what they are measuring. Next up, pressure. This is the force acting on a specific area of a surface. Think of a deep sea diver. The water pushes on them from every single side. That's pressure. 1 atmosphere is the standard pressure at sea level. It's over 100,000 pascals. Believe it or not, the air around us is pressing on us all the time. We just don't feel it. In chemistry, accuracy is everything. That's where significant figures, or sig figs, come in. Rule number 1. All non-zero digits are significant. So 452 has 3 sig figs. Rule 2. Zeros sandwiched between non-zero digits also count. 608 has 3 sig figs. Rule 3. Leading zeros never count. 0.098 has only 2 significant figures. But trailing zeros do count if there's a decimal point. 6.0 has 3 sig figs. Accuracy. What happens when your measurements have different levels of accuracy? Follow the rule. If you divide 32 grams by 1801 milliliters, your final answer can't be more precise than 32. So the answer must be rounded to only 2 significant figures. That's 1.8 grams per mil. Just remember the classic analogy. A chain is only as strong as its weakest link. Time to test what you've learned. Are you ready for a quick chemistry challenge? Question 1. What is the official SI unit for temperature? I'll give you 5 seconds. It's Kelvin. Remember, scientists love Kelvin because it has no negative numbers. Question 2. Which one changes when you go to the moon, mass or weight? It's weight. Gravity changes, so your weight changes, but your mass stays the same. Last one. How many significant figures are in the number 0098? Think fast. The answer is 2. The leading zeros are just placeholders, not significant figures. Great job. You now understand how scientists measure the world with perfect precision. From tiny atoms to the heat of the sun, you've got the tools to measure it all. If you found this helpful, please hit that like button and subscribe for more chemistry tips. Thanks for watching, and remember to always learn smarter. See you next time.